Hello everybody and welcome to my channel. In this episode of Data Analytics Computing, we will go through logistic regression with Python and a brief introduction to classification. As a reminder, in this series of Data Analytics Computing, I do go through some programming concepts as well as some statistical inference concepts. However, my focus is how to run the code in Python and how we can apply these models. If you have not seen my previous video on linear regression, you do not need to see it for this video, as we will go through both linear and logistic regression. However, the link will be somewhere in this screen. Starting with this, first we're going to go through some packages. We are going to need pandas, NumPy, these four models from scale-learn, linear regression, logistic regression, classification report, and confusion matrix, matplotlib, pyplot, and sequel. There is a lot of ways to import from scale-learn instead of the syntax from import. However, this is the one that I prefer personally, but it is a matter of personal preference. We will start importing all of these. After we are sure that we went through, we will perform both linear and logistic regression this time and compare them to put a case for logistic regression. If you do not have the packages, you will need to follow the syntax, pip install pandas, scale-learn, and seaborn from the respective packages. For this video, we will be using the salary screen dataset that you can find on the description link. This dataset is from US technology salary workers, and it has certain variables regarding that. As you can see in Variable Explorer here, we imported this as a data frame with the pd.readCSV function that got from this directory here. There is a lot of ways you can import this. For this is my unique directory that I put the file into. If you put it somewhere else, you're going to need to get the path first and come back and put it into the pd.readCSV function. This is a data frame, and as we can double check with the shape method, it has 19 columns and 1,655 records. If you use Variable Explorer, actually, you can get way more information than that. We can actually get a very brief example and with some colors to say the background color and the column minimum and maximum. We will not depend that much on this right now, though, because this is a feature more exclusive to Spider. If you're using other environments like Jupyter Notebook, you may not have this. We will first get some relevant columns. We could use all the 19 columns. However, in this case, we are only going to focus on these 6. A disclaimer here, there are more advanced ways to see which variables we are more interested with. I will not touch upon them because that will make this video longer than it necessarily needs to be. And I am focusing, as with my linear regression model, on basic logistic regression. There is a ton of specifics that you can go to different sources or the book that I'm putting on the description, An Introduction to Statistical Learning, that covers this model way more in detail and with way more technicalities if you're looking for that. We will subset with these 2 brackets here by name, and we are creating a new data frame that you can also explore here that's called income df sub. This has only 6 columns but the same number of records. Null values. With null values, or NA values, depending on how your terminology works at, we can do a lot of stuff with them. There is a lot of ways to treat them. In this scenario, again, similarly to feature selection, how we are not covering that, we are assuming that you already know what to do with them. We will just use the isName method first, and this will give you a matrix with false whenever it is not null and true when a record is null. We are more interested, though, if we add sum here with the .sum. This is going to give us per column how many records are null. As we can see, employer name has 4 records that are null, total experience years as 47, annual base pay has 4, and employer experience years as 47. This is important because the scale-learn cannot handle those records in this model. We will drop them just because it's only 47 and it is not that much of the data set. So we will go ahead and create a new data frame that, as you can see here, has only 1,584 records. Considering that the original data set was fairly big, we do not really mind losing a couple of records. But again, if you were in other type of situation, you may want to put the average of the column or do some fancy statistics and transformation to deal with those null values. As a final reminder, a null value is just a missing value that you will put there as null. In this case, we will go ahead and create a new variable called high income. As you can see here, the way we create this variable is by putting high income in brackets in the data frame that we want to put it into, income df clean. We are using pd.cat, and then all of this is inside the function. Income df clean is the variable that we're using to get this one. So it is derived from this variable here, annual base pay, and we are putting it into bins or buckets. The first bin is going to be 0 with the label 0. Whichever value that is between -1 and 120K is going to go in 0. And whatever is more than 120K all the way to infinity is going to be in 1. We will do that right now. Now, you may be asking, wait a second, isn't this a numeric variable? It is a numeric variable, and actually needs to be for this to work. We could perform regression here, but we are not going to because we're more interested in classification at this point. Instead, we can also take this variable here and triple check if it worked correctly. As you can see here, the first record is 125K, and here it is a 1. Therefore, it was correctly classified. Here it's 65K, that's less than the cutoff value that we set here in the bin, and it is 0 here. So it worked correctly. We can see the columns just to triple check that we have the new variable. As you can see, high income is there. We can also just get a brief preview of how it looks like. Perfect, it does work. We will be using employer experience as our predictor, as you can see here. If you are used to all the terminology, predictor, X variable, or your independent variable is all the same terminology, at least for these models. High income is our prediction, Y variable, or independent variable, depending on your terminology. What is important to know here is that we are just assuming there is a relationship between our X and our Y. How we can interpret this relationship for this data frame particularly, and these variables, is that the number of years that you have been with a current employer can be used to predict high income. And we want to know that. Can we predict if the position will be high income, a person will be a high income with a certain number of years? That is something that we will discover after performing this model. We will first use our X and declare our Y here. Now, first of all, you may be asking, why cannot we just perform linear regression? It will be very nice, right? If we look at our Y, it's only zeros and ones. It is numeric. So we can perform linear regression, right? It will give us something. And you're right, it will give us something. So let's go ahead and test our little hypothesis that we can just use linear regression. We import linear regression from sklearn and use it here. Then we feed the model. Again, remember, this is a method called feed that just allows us to train the model using X data to the Y variable here. And now we can get the score of that model that, if you have seen the regression video, is just the R-square value. 0.01, not the best that we could get, but that is not the most important problem here. If we go to linear predictions and we just store all the predictions of the model into a different variable, we can look at something very interesting that will happen here. Now, these lines of code here are for static purposes only. We are just defining here the style of the graph, the X label, the Y label, and the title of the graph. You could just use these three to generate the graph that I am about to show, but I want to keep it neat and explain it a little bit better. In the required lines, though, we are graphing first X, that if you don't remember, here is how many years an employee has been with the current employer. Y is our variable. Are you high income or not? Are you above 120K or not? And this is just the size of the plots. And this is a scatter plot. Next, we're going to use from the pie plot. We are plotting here the X variable again and linear predictions. This is the predictions that actually happen here. The color is going to be black, and we're also going to use line width to just make it a very nice line. And PLT show will give us that graph. That took us to plots here. You can see how we have some values over here, some values over here. That makes sense because everything is going to be between 0 and 1, just by the logic of how we put the bins here. But notice something. Linear regression does some decent job here. You could argue if anything is more than 0.5 predicted by linear regression, we could put this as a high income variable. I think if it's less than 0.5, we can put it as a low income variable. What is the problem with this approach? Well, the regression line is very off. That's the first thing. But this is more important. It goes more than 1. A prediction here with, let's say, 55 to 60 years at the company, it will be above than 1. That does not make sense because 1 is our indicator. If you are 1, you should be high income. This is also because this is a regression problem, not a classification one, but I want to put the point there. This is why we cannot put and use linear regression for classification problems. More broadly, this is the main reason why we have regression problems and classification problems. You may also find regression classified as prediction problems. I prefer the regression label because you can predict things both in classification and regression. The main difference here is that regression works with a numeric Y dependent or prediction, while classification works with a categorical or Y variable independent or prediction. Let me say that again. You will define if you have a classification or regression problem if what you're trying to predict is numeric, that will be a regression problem, or it is not numeric, it is just a 0 and 1, yes or no problem, that will be a classification problem. We will need to use logistic regression for this. We could use other different algorithms, but I chose logistic regression because it is the first model I learned in classification, and its approach is very similar to linear regression, and you will see why in a second with the graphs. Finally, logistic regression is somewhat of a misnomer because it is not a regression model. I know that the name says otherwise, but logistic regression is a classification model. Let's make that clear. First, let's triple check our inference here. The maximum of the linear predictions is 1.11. This puts it above our 1 threshold. You may mention, why don't we just cut here and put it between 0 and 1? There, you could do that, but there will still be some problems with it. Therefore, we will prefer logistic regression. Let's start. Using logistic regression with scikit-learn is very similar to linear regression. We are going to create a variable called log model if we go to variable explorer, and we are going to use it with the logistic regression function from sklearn. We train the model, again, notice here, it is exactly the same syntax that we used to feed our linear model, and that it's something very nice from sklearn that we use a very similar syntax. We are just that feed using X data into Y data. Something you want to double check is the classes. Notice here what sklearn is calling classes are our beans here, 0 and 1, and that is more clear if we execute here. We get an array, 0 and 1. I will not go into arrays and what they are in programming, but basically this is between 0 and 1, and the model is interpreting it as that. This is fine for our model, but you want to always double check that before you perform a classification problem in case you got an inverse and what you wanted to get is 0 and what you do not want to get is 1. It should be the opposite way. What you're trying to classify as correct or your targets should be the ones, and what you are not trying to classify should be the zeros. And you will see more of the reason why a little bit below. Instead of score, first let's get all these predictions into a new variable, and we will use something called the confusion matrix. The confusion matrix is very useful for classification because we can look at the confusion matrix pretty quickly with, again, the confusion matrix function that we imported before from sklearn. What this function does is comparing the Y variables. You can think of these as the true values, the true prediction values, what is in the data, versus the actual predictions, what we are predicting with the model, called log predictions that came from the predict function. For this confusion matrix, we will focus on the top left and the right bottom values. This is the number of records that are ones both on the Y, the actual data here, and the predictions. This is what you will probably know in other environments as the true positive rate. 9 here is what it was classified as 1, but it was incorrect. This is not classified correctly. I will not go into detail of the other values, but this is the confusion matrix. There is a ton more you can do, more reports, calculating things like accuracy, specificity, etc. But for our introduction to classification, this is our most important value because it tells us how many of the records were 1 and are actually 1. We can go to the predict proba function that brings us the probabilities. Notice something, all these probabilities will always add to 1. This is because what this is returning to us is this is the probability that is going to go onto the first class, and this is the probability that is going to go into the second class. For this model, we want to get the positive class probabilities, so we are subsetting these with this syntax within brackets. That means giving me this variable, and if we look at this really quickly, we will only have the second value from each of these ones. That is the one that we're interested in. This is the probability that a value will be 1. Now, I know this is a lot of inference and statistics, so I will go into plotting this. Again, these other 4 labels are just for aesthetic purposes, but if we do this here, this is going to generate another plot. This will help me exploring this a little bit more. As you can see here, These are our predictions, the probability predictions. Contrast this with our linear model, where we could just plot our probability, our actual results. Here we are plotting the probabilities. You can think of this as the model tells me this value here has a 0.6 probability of being of the class 1. That will be high income. How logistic regression works by default is saying if a variable is classified as more than 0.5, we're going to put it onto the 1 or positive class. If it's less than 0.5, put it in 0. This is not that easy to see here because these are the actual values. These are not the predictions of the model. Again, these are the probabilities predicted by the model, but these are not the predictions. These are the actual values. Now, how is this value known? The 0.51 is a cutoff value or threshold. You can actually change this value in logistic regression, but we are not going to go into that for this video. You can compare this by putting the predictions on the y-axis instead of the actual values. So let's do that. As you can see here, I'm doing the same thing. I'm taking plain, then I'm taking years at company, here X, but instead of using my Y, that again, the scatter plot, this is the actual number of years that an employee has spent with their company, I will use the predictions. What the model tells me will happen, that again are based on these probabilities. I will take all of this and execute it together. There you go. Compare these two graphs and you can see why I mentioned that. In this graph, it's clear that whatever is more than 0.5% here, 0.5, my bad, will be classified here or have 50% probability as 1, high income. And what is less than 0.5 will go into the other category, not high income. You can see here that the cutoff value is around probably 13, 14 years with a company. This is obviously a simplification because, as we can see here from our actual data, there is quite a bit of higher-ness here that have been with the company less than 10 years, for example, as it can be seen here. However, this can be fixed usually by having more variables. That is something else that can happen. For this scenario, though, we want to keep it on one variable. One difficulty of having multiple linear regression and multiple logistic regression is that you cannot get these plots. It is way more difficult to plot these predictions as nicely as here in multivariate environments, and that's why I have been sticking to one prediction and one predictor, or one y variable and one x variable. You can expand this to include multiple variables here in X, but I have not done it just because this allows us to get these nice graphs that allows me to explain this. Now, this is the cutoff value. Notice this is still a linear model. The theory behind why this is linear is a little bit out of scope, but you can think of as there is a linear decision boundary here if something is more or less than 0.5. As with linear regression, we can get the intercept and coefficient actually. The only bad part is that we cannot interpret that as nicely as with linear regression. You can see this coefficient here is negative 0.97, and our coefficient is 0.066. There is actually way more behind this coefficient and how to interpret it, called the log odds. Again, you can get way more information in the resources I will put below, especially in an introduction to statistical learning. We can also get the score of the model, but this is not the R-squared score that we get with linear regression. This is the number of correct predictions that we have had over the total number of observations. How we get that? Another way to look at it is with the confusion matrix. We can do some algebra, and then we just take what we predicted correctly over the total number of observations. It differs a little bit, but not a lot. And that is our total number. This is also called as the accuracy. If we want a more detailed report, though, we can get that with this function from sklearn, where it gives us the precision, the recall, F1 score that, again, I will not touch upon it today, and the support. It gives you that from macro average and weighted average as well. Now, remember from linear regression, if you have seen that video, if not, I will repeat it here. We have an assumption in linear regression. The line here can be expanded up to infinity. We can predict things that are out of the original data scope. What about logistic regression, though? Can we predict somebody outside of the original data range? In this case, we're going to take one more observation called 70. This is somebody has spent 70 years at the company. I do not know how they would do that, but it may happen. And that's out of the original scope of the data. This reshape is needed in order for sklearn to be able to do it. We will get this, and we can see our value here. It's an array, and see how it says 1. This means that this was predicted as a 1 by the model. How do we know this? There is an easy way to double check this. We can copy this line. I will put it into my console. And instead of 70, we said that the boundary was around 14, 15 years with a company. So let's put here 10 instead. 0. This is the other class here. This is why it's important to have your classes clear, because in this case, again, my 0 class is that you are not a high income earner. My 1 class is that you are a high income earner. Now we will just convert it to a float to see it nicely. There you go. It is 1.0. It was classified as a 1. And you can actually do this with a lot more data. I just did it with one specific instance because it was just easier for me to do so. Now, before we wrap up this video, we will do one more thing. Up until this point, I have only used matplotlib to show how to visualize stuff. I will also use Seaborn. It's a powerful visualization library built on top of matplotlib that we can use for more advanced visualizations. Seaborn has a very powerful function called regplot. What regplot is going to do is map x and y, that again is our data. X is our independent variable, or also our predictor, and y is our prediction, or dependent variable. This is logistic, meaning that we want a logistic regression here. We do not want confidence intervals. I will not go into that, but that allows you to see the confidence interval in a graph. We also want the line to be orange. And once more, all of these are just labels that I'm adding to the model. For X, I want it to be years at company. For Y, I want it to be the predicted high income indicator. And the title is going to be Logistic Regression Visualization. Let's do that. We do this as sns.regplot2. And this is the famous logic function. Here you can see how the value of each of those probabilities fits nicely here. We saw this curve already here, but here we can see it continuously. If you just type in Google linear regression and logistic regression, for linear regression, the best graph that you will get is this one. You will only get a line with your points. Obviously, in this case, it's a classification problem, but you will get a lot of points on the graph and then a line going through them. The same is true for logistic regression. However, in this case, notice the curve of this line. This curve is special because this means that the curve through the logistic transformation and you may also hear in other literature the signal function, it is always going to be bound between 0 and 1. We will never get a value from this curve that is outside of the 0 and 1 range. This is very special because it allows us to use this model for classification. This is why logistic regression is related to linear regression. It is linear on the combination of the values, yes, but it will always be constrained between 0 and 1, where 0 will be this is the negative class and this is the positive class. It will always be contained between them, and that is one of the beauties of this model, that you can actually visualize it and it's not a black box. You can go through the curve and see with the probabilities, as we saw before with the predict proba function, what's the probability that something is going to be classified as either 0 or 1, and also get the predictions as well. With that, I will now end up my video. I hope this was useful. If you have any other recommendations or you want me to cover a specific model, let me know. Give a like to this video if it was useful to you, subscribe, and also keep in touch. Thank you.